The Hilbert-Polya conjecture suggests that prime numbers are not merely a list of integers, but the eigenvalues of a specific quantum system. In this view, the chaos of primes follows the same mathematical laws that govern the subatomic world. This chart compares the zeros of the Riemann zeta function with the Gaussian unitary ensemble, the standard statistical model for the energy states of atomic nuclei. When we overlay these spectral plots, the peaks lock together, showing a shared mathematical signature. The STO axiom arc framework aims to test this connection by building a computational version of this theoretical system. This is the H1200 architecture, a discrete matrix designed to map the behavior of prime numbers into a computable grid. To achieve the necessary sensitivity, the system must scale to 1200 dimensions. This requires translating prime intervals into a massive multidimensional coordinate system. By constructing this matrix, we move the study of primes out of pure number theory. It allows us to treat the sequence as a mechanical system that can be measured, modeled, and observed. Standard number theory treats primes as a linear sequence on a one-dimensional line. However, to observe quantum-like interactions, we must place these numbers within a structured spatial environment. We map prime intervals onto nested E8 geometry. The linear sequence fractures, wrapping around complex polygons. This mapping follows an assembly line, starting with a 24-cell core, expanding through a 600-cell midlayer, terminating at the E8 boundary. This spatial arrangement allows the matrix to test for three specific constraints: the effects of empty prime intervals, the coupling between different dimensional rings, and phase shifts from semi-prime pairs. Treating the prime sequence as a physical lattice is a methodology designed to reveal whether primes naturally organize themselves into the patterns predicted by quantum mechanics. Building the H1200 matrix begins by translating 600-cell geometry into a framework of computable rows and columns. This translation is possible because the 600-cell and the E8 lattice share a specific mathematical identity, a Coxeter number of 30. This identity dictates the structure. 120 vertices divided by a Coxeter number of 30 resolves into 4 rings of 30 slots. To reach the E8 boundary, an E8x double cover doubles these to 8 Petri rings, accommodating all 240 active nodes. These 8 layers, known as Petri rings, form the container for our 1200-dimensional matrix. Within this container, the model applies a calculated coupling gradient that varies across the 8-dimensional layers. The innermost rings possess a fluid, active coupling. As we move toward the outer E8 boundary, this coupling becomes increasingly rigid and structured. This gradient is designed to stabilize the matrix, ensuring that the interactions at the core are grounded by a consistent mathematical boundary. The matrix is populated by mapping prime numbers to specific coordinates. When a prime lands in a designated slot, that node is activated. However, as the numbers grow, the gaps between primes widen, leaving the majority of the matrix slots empty. These prime deserts form Voronoi voids, geometric gaps between the active prime nodes. The architecture accounts for exactly 9 of these deep hole voids for every active coordinate. To model this, the system uses a deep hole traversal rule. If a connection between nodes spans more than 1/9 of the average prime spacing, it is flagged as a boundary crossing. Crossing these voids applies a specific impedance penalty to the edge, a resistive cost meant to simulate the difficulty of maintaining a connection across empty terrain. To bridge these resistive gaps, the model requires a 90-degree phase shift. This Euler pi/2 commit is a condition intended to model the phase locking observed in complex quantum systems. By assigning physical properties to the absence of primes, the model forces the data to interact within the spatial constraints of the lattice. While the grid defines the positions, the semi-prime constraint engine evaluates the energetic connections between the nodes. This engine analyzes semi-primes, numbers formed by the product of 2 primes, to determine the geometric tension between the factor pairs. We measure this as SP chord phase. Natural alignments, like a square root 2 factor pairing with square root 1, have 0 tension. But identical density factors, like 2 square root 4 factors, clash, creating maximum structural tension within the grid. To resolve this clash, the model implements a 180-degree phase shift. This is designed to introduce destructive interference between overlapping factors. Incorporating these phase shifts allows the matrix to approximate level repulsion, the phenomenon where energy states in a quantum system resist occupying the same value. Once all constraints are applied, we extract the raw eigenvalue spectrum from the H1200 matrix to see if it matches the signatures of quantum systems. The initial output is highly chaotic. Like many complex systems, the raw data is filled with local fluctuations that mask the underlying trend. We process this using a PCHIP unfolding algorithm. This systematically smooths the chaotic raw data into a clean, mathematically precise curve, allowing us to analyze the distribution of the energy levels. To benchmark our results, we use the Kolmogorov-Smirnov test. This statistical measure tells us how closely our matrix alignment matches the theoretical GUE standard. The results show a clear progression. While the early H30 baseline scores 0.1042, the more advanced H600 Ring 1 architecture reaches 0.3663, a significant statistical alignment with the GUE benchmark. This alignment suggests that the geometric rules we've implemented are successfully capturing the spectral behavior found in actual quantum mechanisms. For a final validation, we look at the DR combo counts. This test compares how real primes distribute across the E8 framework compared to a standard random model. We map 10 million real primes into the spatial combinations dictated by the E8 structure to see if they follow the expected geometric patterns. If primes were distributed randomly, their presence in these specific geometric categories would be relatively flat and predictable. For one category, combo 28, the random model predicts an average occurrence of 860 instances, but the real-world data shows a massive spike. Instead of the predicted 860, the real prime dataset contains over 10,000 instances of this specific configuration. This produces a z-score of 36.1.49. At this level, the probability of such a result occurring by chance is so vanishingly small that the random model of prime distribution becomes statistically untenable. This high confidence alignment indicates the prime sequence is not a stochastic series. Instead, it exhibits a structural organization consistent with high-dimensional crystallographic geometry.